a quick introduction on what really MBD is and why should we do an MBD analysis, how to do MBD using Altair HyperWorks, and who is using Altair HyperWorks for MBD, so that you have an idea of what you're going to work on. So what is MBD? MBD stands for Multi-Body Dynamics, and as Wikipedia says, it's a study of dynamic behavior of interconnected bodies, each of which may undergo large displacements. Now, as you can see from the definition here, the key words really are dynamic behavior. So we are studying the dynamics of multi-body, many bodies which are connected together. Alright, and also large displacements is a point to note there. We are dealing with bodies which are connected in such a way that there is some relative motion between them. So typically when you are going to deal with an MBD model, you would see bodies like this in the figure. You have many bodies connected together by constraints, and you could be applying some motion on one of the links, and there could be some forces acting and so on. And more often than not, you will be dealing with rigid bodies, because here you're dealing with a study of the system level behavior, unlike in FE where you're more interested in a local area. So since we are dealing with rigid bodies more often than not, this also means that the simulation is very quick, and this also means that you can do more number of iterations to come up with a very good solution for your system. So why do MBD? If you want to analyze mechanisms, there are kinematics and kinetics. If you need forces for durability analysis, there is also an option of converting some of the rigid bodies to flexible bodies and extract loads. You can study cases where large motions involving contacts are involved, and you could also perform vibration studies and many more really. And MBD can apply in any of these industries that you see here, and if it moves, it is an MBD application. So how to do MBD using Altair HyperWorks? In a typical CAE scenario, you would start with building the model, you would test it, you would review the results, and you would think of improving it. So to build, we have Altair Motion View, which is the MBD preprocessor that Altair has to offer, and it works in tandem with Altair HyperMesh, which provides good support for giving CAD designs or FE models that you want to import. And also you could typically build an MBD model in HyperMesh as well, but Motion View is the celebrated preprocessor, I would call. And once you have the model built, you would like to test it, and so the solver for MBD from Altair is called Motion Solve. And if you have flex bodies being modeled in your system, you could also use Altair radios to model those flex bodies, and they go in as inputs to Altair Motion Solve. And once you have your solution, you would like to review the results, and these are post-processed in Altair HyperView, which is the animation client. You can also contour for forces or displacements and so on. And you have Altair Hypergraph, which is the plotting client. You also have Hypergraph 3D for 3D plots, waterfall plots, and so on. And you have Altair HyperStudy, which is a common environment where you can actually analyze multiphysics, and you could do design of experiments, stochastic studies, optimization, and it's really a neutral model which can read a variety of input formats, and and it can help you in carrying out iterative improvements to your model and come up with an optimal solution. And we have Altair OptiStruct, which has already gone places because of its ability to optimize your components, their material, the mass reduction, and many more things that it has to offer. So who is using Altair HyperWorks for Mbd? As you can see, most of the big names that you can think of are using Altair HyperWorks for Mbd. Porsche, Toyota, BMW, all of these are recent acquisitions, and you have the formula teams like McLaren as well. So you can be assured that you're in safe hands if you're using MotionView, MotionSolve for Mbd. And really, more than 150 companies use Altair HyperWorks for Mbd. So now that you have a brief idea about what Mbd really is, I would like to explain to you what the Formula Student Vehicle Library has to offer. What's the formula? It has fast and easy to build models. So though I would recommend that you have some training on MotionView, MotionSolve, but that's not a prerequisite to use this vehicle library, because the way it is being offered to you is you typically just assemble systems together in just a few clicks, and you're all ready to run events on it and analyze the results and do optimization. And it also has some standard report templates that you could use to study the parameters like caster, camber, toe, and all these other design factors that the automotive industry would be interested in. And using the advantage of HyperStudy, as I had told you earlier, you can also optimize the suspension geometry of your front suspension or anything for that matter. And then you can export loads by requesting for forces on one of the components, and these loads can be exported in FE format for further FEA analysis. So that is the formula we are talking about. So what does the library comprise? It has the vehicle body. You have one system for half and one for full vehicles. It has the front suspension system, steering system, rear suspension system, a drivetrain system. You have analyses or events that you want to study, and it has some spring tires if you want to study the full vehicle behavior as well. So we are really talking about systems when you're using the vehicle library. So I would like to give you a brief on how systems really work. A system is a container entity. So as you have seen, an MBD model would have many bodies connected together with joints. So all these are located at different points, and you would have motions, forces, you will have graphics to represent the bodies, and so on. So all these things can be stored in container entities so that you can reuse them in other models or do common operations. So you can organize your file modularly, you can reuse system definition files, you can easily debug and maintain your files, you can create a library of modeling components, which is what we have done with our Formula Student Vehicle library. And we can perform certain operations on the entire system at once. I think it's a good idea to show you how the systems work in motion view. And this is the motion view environment. This is how it looks like. And the building process is fairly simple. You just right click and you can add entities that you want. So I can create a point just like that, right click, add, and I can create a body. I can enter its mass and inertia values. Specify its center of mass. I can represent the body with a graphic. Let's represent this body with a sphere which is located at this point. Okay, so what have we done now? We have a body entity, we have a point entity, and we have a graphic representing it. So what systems can do is what I will be showing you now. So if I add a system, and I will like to transfer these entities into the system now. Okay, so all the entities that I created are now located in the system. So the system contains these entities, and I have the liberty to export the system in an MDL format. Let's call this system example and export. And now what I can do is I can reuse this particular system definition in either other models, or in the same model I can instantiate it multiple times. So I'm going to import the same system here. Maybe give it a different variable name, call it system 2, and I can use the same system again. So I'm going to import it another time. Okay, so I have 3 systems here, and I can as I said earlier, carry out operations on the system as a whole. So if you can see, it's the same system that I have instantiated it multiple times, and I'm reusing them basically. So this is what we are offering to you as well. in the form of systems for steering, suspension, and so on. So I hope that gives you a good idea. And drawing analogy to the programming language, systems are like procedures. So suppose you have a procedure called summation a b, which will accept variables a and b, and it will give out the sum as the output. And there is the main program which is calling this procedure here, right? So similarly, we have a main model, and this is importing other systems and combining them together to make a main master model that you can proceed your work on. All right. So what can you model with the formula student vehicle library? You can model the front half car, rear half car, the full car without powertrain. So let me actually show you what systems you need to select to assemble the front half car. You need the front suspension system, you need to select an analysis, a steering system, and the vehicle body, and these would together form the front half car. And you can carry out the following analyses on this model. Similarly, for the rear half car, you have the vehicle body, rear suspension system, drivetrain system, and the any of the analysis. And you can carry out these analyses. Keep in mind the sequence in which you select these systems does not matter. And you have the full car without powertrain, for which you are going to use all the systems given to you, and they all form the full car. And you can run a 2D road event on it, and also do a typical 4-post analysis. Alright. Before getting into this slide, let me actually show you what you will be getting in your Altair University website. So this is the set of libraries, and you can see that there are systems for the tire, the vehicle body. So it has a half car and a full car. You have the steering system, and there are also some demo videos that you can refer to, which will give you which will explain how to build models to suit your need. So it's all going to be there, so you need not worry. So as I told you, hyperstudy is a multidisciplinary DOE, which is design of experiments, optimization, and stochastic studies environment, and it has a user-friendly interface. It has an extensive expression builder for mathematical operations, and a very good and robust optimization engine, which is what we will be using to optimize our suspension. And you could also do some built-in post-processing to study the results. So this is how motion view model will interact with hyperstudy, and any of these studies can be carried out and post-processed. Now we will be seeing a demo of how to use this vehicle library. Before that, to give you a brief, the objective of this demo is to show you how to perform an optimization study on your front suspension model and export loads for FE format. So what we will be doing here is choosing the inner and outer tie rod points and decide on the optimum coordinate positions, rather allow hyperstudy to determine these optimum coordinate positions to achieve a target toe curve. So when we are talking about a target toe curve, this is what we have. So if you are given a curve like this, which is wheel vertical displacement versus the toe angle, this is what you want your toe angle curve to follow, or at least be close to. And why did we choose these points? Because these points will have direct effect on your toe angle. Toe is basically the angles that the wheels make with your vertical when you're looking at the car from above. So the angle of this toe will directly affect the handling of your vehicle. So it is a very important parameter that you would want to consider. The demonstration is divided into four parts. So first I will be showing you how to assemble the model in the first place and carry out an analysis on it and look at the reports. Then I will be showing you how to use hyperstudy to set up a study and perform optimization on your model. And then we will export loads for FE format. So let me bring up a new session. So if this is how your motion view model will look like, what you need to do is select model, and as I showed you earlier, go to the import export tab and browse to the vehicle libraries that are given to you. So I need a front half car, so I will be selecting the half car system definition and import it. And I need the front suspension system. I'll select that one and import. I need a steering system. So I'll import that one. And we need to attach an analysis, as I had said earlier. So I go to the analysis folder and under front car analysis, I can select any of these analysis. So let's say static ride. And this is important. Whenever you are importing an analysis, when you click on import, don't forget to change this to analysis. So say OK. Okay, so now we have four systems which are really independent of each other, but there are actually some references which we need to resolve. So systems interact with other systems through what are known as attachments, and this has been taken care of in the system definition. So what you need to do is resolve these attachment entities. And to do that, you need to select model, right click, apply attachment candidates, and then you can see that everything is resolved now. If you go back to each of these systems, you will see that all the attachment entities are resolved. So that's how you set up a model with the analysis. And if you notice, each of these systems has many bodies at many points. It has some graphics, joints. So all of these, and it also has subsystems. So all of this is possible only because of the power of systems, which is unique to Motion View, Motion Solve. And the next thing that you would want to have control over as a user or somebody who's trying to improve his model or perform some study is to change parameters. The most common parameters that you would want to change are they are organized in these entities called datasets. So for a full vehicle dataset, you have the vehicle velocity, the rotational velocities of the wheels, you have the vehicle parameters, the type of suspension, the static loaded radius, etc., the suspension travel. So let's say, for example, we make the jounce and rebound travel 50 mm. Okay, so now you have all these systems imported together. You will want to save a master MDL file, which is the motion view model file, and that is done by going to File, Save As Model, and now you can see that the model is saved as master.mdl. And to run this model, you need to go to the Run panel and give it a name, say master again. XML is the extension of the solver input file. So if I click on Run, so the analysis is complete, and what you are looking at right now for new users of HyperWorks is this environment is called the HyperWorks desktop, and it has multiple clients in the same environment. So you can also access the post-processing clients in the same environment as my Motion View preprocessor client as well. So if I click on Animate, I can get another window with HyperView loaded in it, and I can expand it like this and show you the animation. Alright, and the next thing that I wanted to show you is, since your vehicle library also comes with the standard reports, as I had said earlier, what you need to do is go to Open Report Template here and go back to Hypergraph Templates and select half car template final. This is for the front half car, and the other TPL is for the rear half car. So this asks for a PLT file as the input for the report template, and you need to select the latest plot file that was created. So that was master plot. So if I select that, and if I say apply, it has a lot of results to show, so it will take some time. And there we go. So if you can see, there are other pages that have been created, plotting all the required parameters that you would want to study, like the steering angle, the steering torque, you have the roll angle, caster, kingpin inclination, and a lot of them, close to 74 pages in all. So you have all that you would want to study and more. So this is how you typically assemble a model from the vehicle library that is given to you, carry out an analysis, and study the reports. The process remains the same if you have to model a rear half car or the full half car. The systems that you need to be using are I have already showed you them in the slides, and there is also going to be some demo videos that you can refer to and some documentation, so it's all going to be there. Now I would want to show you how to use hyperstudy to optimize our toe curve. So as I had told you earlier, we will be choosing the inner and outer tie rod points. Let me show you where they are here. So the inner tie rod ball joint is located in the rack pin steering system. This is the joint that we are talking about. So changing the location of this is going to affect your toe, and this is the outer tie rod ball joint. Changing the location of this is also going to affect your toe. So these are the 2 points that I will be choosing to vary and study the behavior of my suspension and try to achieve the target curve that I have shown you here. Okay, and since I need loads for FE, I need to request for forces on any of the bodies. So to do that, what you need to do is right click, add general MDL entity and output. So this is going to be the body force on the lower control arm. So it's very easy to decide what output requests you want and define them. So I need a force on this body. You can also create them on a joint, beam, bushing, etc. So the body I will be choosing is the lower control arm. Okay, so I will save this model now and proceed to the second phase, which is the study setup. To invoke hyperstudy from within motion view, you need to click on applications and select hyperstudy, create a new study, and select define models. So here you are choosing the input model which you will be carrying out studies on, and you will be specifying a name for the solver input file. So let me call it static write.xml. and you will want to import the variables. These are the design variables, meaning the variables that you will be varying within a certain range to achieve your optimized results. So as we discussed earlier, we will be importing the y and z coordinates of the outer tie rod ball joint and the y and z coordinates of the inner tie rod ball joint. Why am I not selecting the x coordinate? X is by definition along the length of the car, so I don't want to reposition these points in the x direction. I want them to vary in the YZ plane, so I am selecting just the y and z coordinates. So after I have imported the variables that I need, I will be specifying a range within which they can vary. So this range can be given either in terms of a value for minimum and maximum range, or you can also give it in terms of a percentage, and I have decided to vary it plus or minus 10% for all of these. And after doing this, you say apply, and next you will be carrying out a nominal run, and this is nothing but the run of the model at its baseline configuration. So when I click on evaluate tasks, so it gives you the status. And next what we need to do is define the response. The original curve is currently like this. This is the toe plotted against the wheel vertical displacement at the model's baseline configuration, and we are trying to achieve closeness with this target curve, and to do that we are changing the locations of the tie rod ball joints, and this is what we need to define as the response. So you can add a response. The response can be from the file source. So this vector 1 is the actual toe, and so this is my toe, and for the target curve, if you have noticed, the toe is related to the wheel vertical displacement. For point 2 toe, it has a relation as -20, and for point 4 it's minus 40 and so on. So the factor is minus 0.01. So what I'm going to do is, for the second vector, I will select the wheel vertical displacement and multiply it by 0.01. So I add another file source for vector 2, select that wheel vertical displacement, and in the expression I will multiply it with 0.01. So what do we have here? We have vector 1, which is the original curve, and vector 2 multiplied by minus 0.01 is my target toe. So I want to, so this will be same as plus So what am I doing? I am reducing the error between the original toe and the target toe by reducing the error in the square. Alright, so once this is done, I say OK. So this is going to be my response, and later on I want to reduce this. That will be my objective when I'm going to do optimization. So you click on evaluate expressions after that, and you have some statistics and 2D and 3D scatters as well inbuilt, and you have a report that you can generate. So once you are done with this, that completes the second phase, which is study setup. The third phase will be to carry out the optimization. So to carry out the optimization, all I need to do is say next, add approach, select optimization. So I am defining my design variables from the study setup. I have given the range in which they can vary. I'm selecting the response. So I need to define the objective here, which will be to minimize the response that I created in my previous step. So this was the response that I created. So I say apply. Next, I will be selecting an algorithm for the optimization. And after I do that, if I say next and actually click on evaluate tasks, it will carry out the optimization process, doing multiple runs for each of the combinations of your coordinates for tie rod ball joints. And I wouldn't click on evaluate here because that's going to freeze my screen. It approximately takes 5 to 8 minutes if I remember. Since I have already recorded this process in a video, I'm going to show you what happens after that. So after all these runs, this is what you would see. You will see the status of all the possible combinations that it has carried out, and it will determine what's the best configuration. You have all the data that you require to study in there. And if you notice, this was the objective that we defined. 42.62 was the difference that we got between the original configuration and the target toe, and the run number 18 is what it has found to have the minimum objective value, which is very close to 0. Hence, this will be the run that we will be interested in, and these are the coordinates that we are interested in. So you have histograms and 2D and 3D scatters, and that is the process really to carry out the optimization. So let's review the model after saving this XML. So in the video, I'm plotting the original configuration first. And now we will be going to the folder run number 18 and see how the curve has changed. So that's run number 18. And that's the folder created with all the runs. It saves the model file as well with the changed configuration, so there is nothing that you need to do really after running HyperStudy. Yeah. So you can see the original toe and the optimized toe, which is very close to the target toe curve, and that is what we wanted. And after that, the last part is exporting load for FE. After you have requested for forces on the control arm, it will have created a meta file that you can use. Before that, let's look at the difference in the configurations before and after optimization. Let's see how the suspension geometry has changed. So you can see the difference in the geometry there. So now if you go to Flex Tools and Flex Prep, load export, you have to go to run number 18 and select the meta file that is created there. Select the four components, decide on what time steps you want the load set. You can export a tabular summary or export it in OptiStruct or Nastran format. So this writes out a dat file, .dat file, that you can import directly in Hypermesh. You also have options that you can see to export the dat file after or before giving prefixes to the node IDs. So once you say export, the dat files are exported and you can import them directly into Hypermesh. Alright, so that completes the demo. I know it's a lot of stuff to take in one go, but if you actually go through the demo videos after this, you will have a good feel for what you will be needing to do to go through this process and take advantage of the integration and the variety of tools that HyperWorks has to offer. And this is what McLaren has done too, and this is a case study in which McLaren wanted to simulate the suspension response of a high-performance sports car, and it wanted to consider effects of suspension compliance characteristics, and it wanted to carry out optimization and achieve performance targets, and of course it wanted it like any other OEM would do in a quick and cost-effective manner. And when it approached Altair for a solution, thankfully we had Motion View, which they used to create wizards and build the models in a speedy way. And we had Motion Solve, which they used for a fast, robust and accurate analysis. And using HyperStudy, they optimized the suspension hardpoints, as I just showed you, and also the compliant push rates. So it is not necessarily only the hardpoints that you can optimize. You can pick and choose what the design variables are, or whatever you want, and optimize them based on your needs. And the benefits: it helped McLaren dramatically reduce the development time, costs, and improve the end product at the same time. As you can see in the plot, the the steering angle and the camber angle before and after optimization. So I would really urge you to take advantage of this, and with that I conclude my presentation and hand over to Jacqueline.
Thanks, Jim. Yeah, I think just one additional thing to point out is that with this case study in particular, that I think the Formula student teams can really relate to needing to come up with a quick and cost-effective solution. They have to work within a budget and build a new car every year, and then also they want to win the race and do well on the dynamic testing aspects. So it's also important to have a really good working suspension setup. So with HyperStudy, they can either look at a single response like the toe angle curve that you've presented, or they can look at optimizing multiple variables in the system and have multiple objectives within HyperStudy. So with that, we'll say thank you and open the floor for questions. Just as a reminder, if you'd like some more information about Altair and HyperWorks, you can go to altair.com. And remember, Altair University is where we will have the videos, training materials, and model files for the vehicle library. So that's the Altair University Training Center. And then if you have any additional questions, please email us at altairuniversity@altair.com. And that's a good way to contact us about team sponsorship as well, if you're interested in using the full HyperWorks suite for your design and simulation needs for your Formula Student team. So thank you for your attention, and we'll go ahead and close the webinar now. Thanks for attending.
Thank you.